probability and classification. And there are two parts. The first part, I'm going to talk about the feasibility of learning and what the concept of the generalization of the classification is, and finally the VC bound, which is a very essential theorem in the classification. And in the second part, I'm going to talk about the optimal Bayes classification and some of the non-parametric probability density estimation methods. So prior to move on, I just want to first mention that my English is not good, so please be generous for my poor English skills, and please understand if I use Korean from time to time. So, firstly, if you think about two-dimensional data, which means you have two features, and the classification is like this. You have two kinds of labels. So if you want to classify this kind of data, probably you like to find this dividing line and classify this side as circle ones and classify this side as cross like this. Okay, this is fine. Everybody's fine with this method. So then, why do you think this works? Why? I mean, it's a training data set. You already heard about what the training and testing validation is in the first class, right? So you're only given a training data set, and you fit the line from the training data set. But why do you think this line classifies well for the testing data set? Because you have some kind of belief in that this kind of weird situation does not happen. For example, this is your training data set, but you don't expect this kind of testing data set, right? You have some kind of regularity in the data set, so you can generalize to this kind of pattern can be generalized to the testing data set. Or you probably expect that you have trained this set here, but all your testing data set is like here. The class is not reversed, but you don't expect this kind of testing data set. If you have this kind of testing data set, if you move the classification line just a little bit, will significantly changes the way the way the classifier works on testing data set. Right? So you don't expect this kind of testing data set or this kind of reverse testing data set. So this makes the fundamental assumption on the machine learning and the classification. Every single machine learning algorithm works on the premise that some kind of regularity is in the data set and you can model, and the classifier can be generalized to the testing data set. So I just want to briefly talk about how the machine learning works. So there's always which makes the training data set, training examples. And training examples are pairs of x and y. There's a known target function. And these two are combined to the training example. So you have a known input distribution. There's no this kind of things happens. So if you have a roughly x distribution here, and the testing data will be also generated in this distribution. And there's a known target function. These two are all unknown, can be represented in the implicitly represented in the training examples. So there's a known target function. If you're given x, then f, which is unknown, but will give you the answer y. So you don't know all the pairs, but you have some of the pairs, n number of training examples. And your learning algorithm and you have possible candidates, which is called hypothesis. And so you need to first assume your hypothesis set. You need to first model the hypothesis set. For example, here I modeled that one single line can separate two different classes. That's the hypothesis set. So for this example, H is the set of different lines, and some kind of learning algorithm will find among the hypothesis set using the training examples that the learning algorithm will find the best hypothesis. So this will give you the final hypothesis. And our objective is to make Gx similar to X. And you need to also notice that X here will be generated from the known input distribution. This is the typical setting where every classification algorithms assume this kind of framework. Actually, if you further generalize this one, here it's f is a deterministic function. But if you generalize further, which I'm going to talk about in the second part, it's not the deterministic function, but the probability function. But from the time for this time, you can just consider this as a deterministic function. Do you have any questions so far? Any kind of questions? Inquiry? So, what do I mean by the X data is generated from a known input distribution? Px here is the probability density function, or probability mass function, but I'm going to use the probability density now. And do you know what the IID distribution is? Did you tell them? First class. So the concept of the data is generated from this PX or PDF is that the individual X examples, X1, X2, 3, so are generated from PX in IID manner. IID means independent. Identical. I don't know which one is first. Identical. These two. This is very essential for every machine learning algorithms. This concept. So let's think about tossing coins, example, which is very common. I guess everybody already heard about what the coin tossing is. So there's only two kind of events can happen. You can get head or tails. 가면 또는 뒷면. And if the variables are identically distributed, which means that this means that if you toss the coins multiple times, you will always have the same probability of getting head. Even if the coin is biased, so you will get 70% of time the head and 30% of time tails. Even if you have that kind of biased coin, if you toss multiple times, you will always have the same probability, 70% and 30%. That's the meaning of the identically distributed. And the independent means that if you toss coins multiple times, your first outcome will not change or affect the second or third coin flips. So that's what independent means. So every single data will be generated in IID distribution. So you don't know what exactly the distribution is, but you assume that you have identically distributed and the individual training examples are not correlated. It's independent. That's the illusion of IID. Do you have any question? And actually, so far you can find in the internet quite easily what the concept of these things is. And from now, I'm going to talk about more complicated things. So, if you have any questions.
Yes. Could you tell us again about the role of hypothesis set?
So hypothesis set is like you cannot always assume the whole possible hypothesis. you have some specific kind of hypothesis. So for this example, there can be infinitely many kind of hypotheses. So here I assume that the class separating line is line, it's a straight line. But you can also assume that this kind of curved lines, and you add this kind of hypothesis into the hypothesis set, and there are many different kind of things. But you have to choose between this or a much simpler set or much complicated set. That makes the if you choose a simple hypothesis set, you may not achieve 100% classification like for this kind of example, because there's no line that can separate perfectly this kind of training data set. But that's not bad. I guess first seminar you already talked about what the overfitting is. So if you add some kind of curved classification line to the hypothesis set, you may be able to 100% classify this kind of data set, but that's not always good because you can overfit it, and this can be just a waste. So you always have some kind of confined hypothesis set.
So hypothesis set is determined before we see the data, actual data.
Yes, but you have some kind of knowledge or your heuristic on the on the data. So if you have image data, you define hypothesis set to the convolutional neural network, and if you have some kind of set of discrete features, you may choose the decision trees. So you can see this as a model. What kind of model you want to pick? That's the different sets of. 그러니까 이거는 그냥 어떻게 모델 셋을 어떻게 정할 거냐. 그러니까 이제 뭐 똑같이 라인이라고 해도 이 안에 수만 가지 라인이 있는데 그것들을 이제 하나의 셋으로 보는 거고, 이제 더 복잡한 셋을 만들 수도 있지만, 그래서 어쩌면은 모든 머신러닝 알고리즘을 하나의 셋으로 넣을 수도 있지만 이게 항상 좋은 건 아니고, 항상 이 데이터는 뭐 리니어 클래시피케이션이 될 거야 하면은 이제 리니어 모델을 정하고 이제 이걸 돌리는 거고. Okay. Now let's move on to very important theorem, which is everything's equal. So you have multiple random variables. Which are independent to each other, but not necessarily identical. But we only consider the identical distribution. But I just want to mention that Coefficient inequalities can be applied to the more general case that these x's are not from the identical distribution. So the only necessary condition is the independent random variables. And what Coefficient inequality says is that here xn is this inequality is a key inequality to derive the Bethany-Cherokee inequality. So, here you have, you can think that you have n number of data, large n number of data, and those data is generated from the dependent distribution, independent, actually identically distributed way, and you have x bar, which is just a sample mean. We usually call this one a sample mean because you have n number of training samples and you have just average. And here the expectation E is actually expectation on the unknown true distribution. So you cannot actually calculate this expectation here. It's from unknown distribution P, which generates the training examples. So this means that you have x bar, which is sample mean, and expectation of the x bar, you can think of this one as a true mean, which is the expectation of the unknown but fixed data generating distribution. And the difference between these two, you take the absolute value, and what this term means is that the probability of this difference, the difference between sample mean and the true mean, is bigger than some small value epsilon, is smaller than this value. Okay, it's kind of confusing if you first look at this equation. So I'm going to explain you again. So basically what we want to do is minimize the difference between these two, because this means is that here this is your training samples. So previously I talked about that you assume that some kind of regularity is in here. So the testing examples will not be here, or reverse this kind of way. So what I'm going to talk about in this Things inequalities is about this. So the true distribution, maybe that kind of distribution can be true distribution, but that the inequality says this cannot be possible because your sample distribution and your true distribution is not so much different. Not so much different. So this value is not that big. So it's not that big because the probability of getting this one bigger than epsilon is exponentially smaller than this value. Agree? And if you look at this term more in detail, if you have large number of n, if you have a larger number of a training example, this term goes to smaller. And then this probability gets much smaller. So the probability of getting big error, then epsilon gets exponentially smaller if you have a large number of data. Actually, I'm so sorry.
That's the notation of true mean.
True mean, yeah.
Could be replaced with just x. Why does it have to be x bar?
Yes, that's a good question. But it's kind of made up for to drive this inequality. You can replace 이미 그러니까 의미상으로는 대체를 할 수 있는데 일단 여기서는 요거를 써야 해요.
좀 궁금한 게 있는데요. 아이덴티컬이 있었는데 인디펜던트는 이제 X1이랑 X2가 진짜 독립이라는 얘기니까 독립하고 얘기 되는데 아이덴티컬가 딴데 스펠셀이 아이덴티컬이라는 게 무슨 말인가요?
여기서
예.
그러니까 얘네들이 identical distribution이 필요하다.
그러니까 아이덴티컬하는 게 아니에요.
그러니까 예를 들면 얘네들이 전부 다 다른 그 확률을 가진 코인 플립일 수 있다. 그래서 identical 할 때는 사실 여기 x바를 x로 치환해도 되는데 근데 지금은 할 수 없어요. 지금. And actually, I forgot one thing. X should be every x I should be between 0 and 1. That's the condition of the quantities inequality. So, do you get the idea why I mentioned the Correctness inequality? So, it's actually the some kind of generalization or extension to the lower law of large numbers. If you have a large number of if you have a large number of samples, if you take the sample average or empirical mean, then your mean will be very close to the true mean. That's the law of large number. And Quetelet's inequality actually quantitatively says how fast you can reduce the error if you grow the number of samples.
근데 그럼 저거는 평균 통계량만 생각하면
So this time is running. I will move on to the next step. I'll define this variable. So I define this psi I, which is to measure for data xi, and for any hypothesis h in hypothesis set large H. This one indicates if this means that indicator function. So you choose some arbitrary H, the hypothesis, then you compare with the true F. Actually, we don't know the true F, but we have the evaluated Y. So at least for training data set, you can calculate this one. So if H and F is the same, you set the value 1, and if not, it's not the same, then you set 0. And you should notice that this psi I is also a random variable. I'm sorry. Yes, it's a random variable, and also the sample average which is this one, is also a random variable and a sample mean of psi i's. It's random variable because x is random variable. X is generated from probability distribution, so x is a random variable. So you take any kind of function, you have some kind of randomness in this value, so it's a random variable, and it can always have 0 or 1. So it matches to that condition, and the difference is it's always in between 0 and 1. So let's say this is the sample mean of size. Then you can apply difference links inequality such that and then if you look at this one very carefully, this is actually error of the classification. It's actually empirical error. So I'll define this term as E in and this term as E out. So this is actually a training error, but I'll use the notation E in because it's an in-sample error. It's also called in-sample error, and this is called out-of-sample error. So if you have training samples, this is the empirical average, so it's an in-sample error. And you cannot see this known distribution, so it's not in the samples, so it's out of sample error. So you get the idea. Do you follow that this is a training error? It's a number of mismatches of from the training data It's number of mismatches of your hypothesis. So that's
저 지금 맞으면일 틀리면 열려서 에러가 아니라 어큐러시.
네, 잘못 쓴 것 같아요. 그렇죠? 잘못 쓴 Do you have any question? You can ask me in Korean.
그럼 저 평균 그걸 씌웠을 때 그 의미가 어떻게 달라지는지 한번 설명해 주시죠.
Expectation. 그러니까 이거는 so this expectation is taken over the whole distribution, the unknown distribution. So you can, in principle, think of this as a test error. Test error is just a proxy for this term. So if you want to truly calculate the true error, then you have to think about the whole possible data. So that it's taken over. But in concept, you can think of this one as a test error. So we want to you train really hard on the training data set, but what you want to do, what you want is to get the difference between these two is small, right? 트레이닝 열심히 했는데 테스트 에러랑 완전 다르면은 전혀 쓸모가 없잖아요. So you want to minimize between training and test error. So okay. And in fact, this inequality is calculated for H, a single arbitrary hypothesis. It's not the optimal hypothesis you get from the training. It's just a random hypothesis. What this means is, even if you choose random hypothesis, you can get this inequality. But what is more meaningful is that if you use learning algorithm to train the hypothesis, and you get the best hypothesis, final hypothesis G, which is also in H. Then you want to find some kind of inequality for this final hypothesis G. So what you can do from here is that you write down the same inequality for every hypothesis. So this is for hypothesis 1. Maybe you can write down like this. And if you write down the same one here. You get the idea. So, if you sum up for every hypothesis in your hypothesis set, then you will get this one. Smaller than 4n hypothesis. Which is some sort of summation here. And which is smaller, which is larger than this one. We're almost there. There means the preceding inequality. So I'm just gonna repeat this again. So psi is just a random variable. It's related to the classification problem, but it's just a, you can think of this one as just a random variable. This value is between 0 and 1. So you can, and it's independent because xi's are generated from independent and identically distributed distribution. So you can use the Grafton's inequality for this random variable. So you can just write down here, it's here, and psi I is defined for specific h. It's arbitrary h. So you can write down this inequality for h. And if you have many number of hypotheses, so if you have a classification problem with the straight line, you have many candidates of the lines. So maybe you have large n number of different hypotheses. So you write down for every hypothesis element in your hypothesis set, and you just add. Then it's actually the union bound for m inequalities. So if you add all, on your right hand side you will get 2m times exponential dollar, right? And on your left hand side you add this one, these terms, and if you add every h, and your optimal g is also in h, so among these events you always have g in h1, h2, h3. So that event, the probability of getting this or this or this or this is bigger than you get this for g, single g. So you can use this inequality here. And g is your optimal hypothesis, at least for your the hypothesis in your hypothesis set. And let's write down this. but you should feel very uncomfortable with this derivation because it's too loosely bounded, right? You want some more tighter bound. In fact, the number of hypotheses in your hypothesis set, even if you choose the linear, the straight line classifier, you have infinitely many number of hypotheses, right? Because it's a real number. So n will be infinitely large. It's infinite. Then your bound is just meaningless, right? So you should somehow fix this number n with some effective number of n. And we're going to replace this one with the VC dimension. That's what Bethany and Sherman has contributed to this equation. And before getting into the details, I'll just change this equation out just a little bit. So let's set this one as delta. Note that this one is small. And I'm going to just flip a little bit. I'll flip this inequality so that you get is larger than 1 minus delta. So we can just prove it. As this is a probability, you can compute this one as 1 minus delta. I mean, the event of this one is larger than epsilon. The exact inverse of this event is this one. So if you have equality here, then your probability will be 1 minus delta. And as this one is inequality, you reverse the direction. So what this means is that, and I'll replace this one with the notation here. The in-sample error, the difference between in-sample error and out-of-sample error, or if you want, the difference between training error and test error. The probability of training and test error, the difference between training and test error is smaller than epsilon. So this is a desirable situation. Is larger than 1 minus delta, and delta is small. So most of the case, you will get this situation. So it's very good inequality, right? I'm going to focus on this here, and you will get this one. First, so what this means, what this equation means, is that at least for 1 minus delta probability, you have this situation where E out is the test error is smaller than training error plus some small value epsilon. So what this means is if you train harder to minimize the in-sample error, E in, then your out-of-sample error is, is quite small. It's not exactly smaller than training error. That's a weird case, right? Test error smaller than training error is kind of weird case, but it's at least smaller than epsilon, so it's kind of reasonable inequality. I removed the absolute operation, so but I'll skip the second case that absolute value is worse, because this is what leads to the free signal.
저 질문 왜 지금 2m, 2-2n 에필론 제곱이 지금 바운드인데
네.
사실 왼쪽 이야기만 보면은 저기 1에다가 g를 넣어도 되는 거잖아요. 그러니까 m이 안 들어가도 성립을 원래 해야 되는 분지가 아니에요.
네, 맞아요.
네, 그러면은 저 바운드를 m을 가져갈 필요가 없을 때는 저 바운드로 이야기해도 되는데 왜 오른쪽으로 넘어갔는지가 궁금합니다.
그러니까 우리가 G를 지금 상황에서 확실히 알고 있는 게 아니라 이 트레이닝 러닝 알고리즘을 통해서 G를 찾은 거기 때문에 이걸 딱 G가 뭔지를 알고 이렇게 쓸 수가 없어요. 그 G에 대해서도 당연히 만족은 하지만 G가 뭔지를 모르기 때문에.
그러니까 왜 저희가 뭔가 G를 구해도 사실 어느 정도는 아비트러리한 G를 구했다고 생각해 볼 수 있잖아요.
그러니까
러닝 알고리즘이 아비트러리하면 그게 깨진 건가요 지금?
G는 이제 항상 옵티멀 해야 되고 옵티멀 하는 걸 G라고 정의했기 때문에
트레이닝이 됐어요.
네. 그러니까 지금 왜 이걸 덧셈을 해서 구하느냐를 여쭤보신 건데
사실 지금 이야기만 따지면 그게 깨질 방도가 없어 보여서
그러니까 우리가 G를 알고 있으면 그걸 계산을 할 수 있는데 G를 모르기 때문에 유형 바운드를 구하는 거예요. 그러니까 G가 존재한다는 건 알지만 지금 이런 트레이닝을 하기 전에 이 바운드를 구해보고 싶은 건데 단지 우리가 하이퍼스테시스 셀만 정해놨을 때 그랬을 때 이 바운드를 구해보고 싶은 거라서 그러니까 G를 지금 모르기 때문에 이걸 간접적으로 바운드를 구하려고 저렇게 덕셈을 하는 거예요. 그러니까 지금 뭐 H1은 뭔지를 정해놓은 거고 이 중에 G가 뭐일지는 모르는 거죠. 그래서
일단은
저기서 뒤집었을 때 원 마이너스 델타 왼쪽이 부등호가 저기 등호 사인이 포함이 가나요?
네, 이거의 반대나 그러니까 이 이벤트의 완전한 반대는 이제 뭐죠? 그래서
근데 완전한 반대는 그 좌하고 우항 사이에 있는 부등호 없어지 부등호 표시가 빠져야 되는지
여기는 그냥 단순 뺄셈이라고 여기가 지금 이니퀄리티가 아니라 이퀄리티라고 생각해 보시면 여기를 지금 부등호 때문에 헷갈릴 수 있는데 이거 그냥 는이라고 생각해도 되잖아요. 이거 이벤트를 요거의 완전 여집합인 이벤트는 요거는 맞잖아요. 그러면은 요게 확률이 델타면 여집합에 대한 확률이 1-4라고 해야 되죠. 그러니까 등호는 유지가 될 거고 그래서 부등호는 So, and we define this delta, so you can calculate what the epsilon is in terms of delta. So here, this delta is this number. You can compute that this one is
뒷면으로 연결되는 게 epsilon
because we define delta is equal to this term, you can inversely calculate what epsilon is in terms of delta. So you just use simple calculation, you get epsilon is this one. So finally, we got the Christie inequality with this concept. So I'll write down that inequality again. E out is smaller than E in plus 2 n over delta. In fact, you want to replace this n, so I'll skip the details, but actually the VC bound is a little bit different, but very similar. So this is VC.
위에서 어떻게
네, 그거는 설명 안 할게요. 그냥 너무 유도가 복잡하기 때문에. So I'm going to skip this step because it's too complicated. It's too mathematical, and it takes too much time.
혹시 그래도 시간이 너무 많지 않나요? H가 저걸 만족하는 H에 대해서 설명드리겠습니다.
H.
예, 그러니까 뭐 모든 하이프셋이 다 저런 식으로 변형이 되는 거잖아요. 그리고 저게 선형 리니어 리그레이션이라고 리니어 클래시파이어일 때 저렇게 된다는 거거든요.
네, 그렇죠. 제 VC bound는 so VC inequality satisfies when you consider the hypothesis set as the straight line, and there's only the binary class. There are only two classes, and but that's because of this MH term. MH, which is the effective, I mentioned that we want to replace this large n because it's not tight. So we want to reduce this number. It could be infinite number of, it can be infinite number, but we want to reduce to the effective number, MH. And Raffling and Sherman is derived MH for binary class and the straight line classifier. And MH is called VC dimension. And you can calculate what this number is, but I'll just skip the VC dimension. So if you look at this equation, then there's n and n. These are the important terms. So if you have a large number of n, your in-sample error, the difference between in-sample error and the out-of-sample error will be very reduced. So if you have large number of training data, then you will have better generalization, and you can always improve your performance in classification because this whole number goes to 0 if n goes to infinity. And another thing is the MH. It's actually effective number of hypotheses. So which means it's roughly speaking, it's complexity of the hypothesis. So it's related to overfitting. So if you have too much complicated model set, if you take too many parameters in your hypothesis, or too much complicated, like not like line, but just curved lines, then if you move on to this complicated hypothesis set, you will increase the number of effective models. So you increase this MH, then you will not get you will increase the generalization. If you too much increase your MH, if you set too much complicated hypothesis. For example, if you want to train a neural network, then if you take too many layers with too many parameters for each layer, then your MH will grow largely. Then your EL, or test error, can be very loosely bounded from your training layer. So you should reduce your model complexity. That's what VC inequality says. So to summarize, I started from just a simple classification problem. Classification is always this framework. All the machine learning algorithm shares this framework, and there's some IID distribution which is unknown, but you know implicitly by training examples. And Hoeffding's inequality says for any independent random variables, so including the PDF for training data, you have some kind of bound that your in-sample error and out-of-sample error difference between those two is bounded by some exponentially decreasing function, and exponentially decreasing according to the number of data samples. So from there, we somehow managed to derive this inequality. So if you have large number of data, you have better performance in the generalization. And also, if you reduce the model complexity or complexity, if you reduce the complexity of the hypothesis set, you'll get a better generalization. That's what this inequality says. Okay. That was the first part. Do you have any question? And second part is very simple, so I will promise I will end in 30 minutes. So in the second part, I'm going to consider a more general case that this f is not a deterministic function, but probabilistic function. So you have some sort of model, which is also unknown. But there's some noise. You can just think of that you label as some noise. So it's not a deterministic function, but you have some kind of probability. So there's a probability of y given x, which means going back to the original example. Previously, we considered that if you have this point, it's unknown, but there's a deterministic function that assigns some class y deterministically. But for this setting, we have some kind of uncertainty of labels. This can be circle or cross. So there's some uncertainty or noise. So for that case, we consider the optimal base classification. Just first consider that just a single feature. And you have two classes. So this is the y-axis is PDF, probability density. And this is the density for x given class this one. Maybe this one. And this one is probability of x given class is 2. Different distribution. What this means, in this example, you have, let's say, circle for classes 1 and then x is for classes 2. Then you have this kind of you get the idea. You have this kind of training examples. That's if you present this in terms of probability density, you'll have this kind of figure. And so let's just for now just assume that you already know the probability density, but it's actually unknown. Is this one and this one is unknown, right? So you don't know how exactly the conditional distribution of these are, but let's just for now just assume that you already know. Then what you can do for the classification for random arbitrary point x here is that just you choose where the probability density is higher. So for example, in this case, red, the density for red is greater than density for purple. So for most of the case, this point will be class 1, right? So you just classify it as class 1. And for here, purple one is definitely larger than the red one. So you classify this point as class 2. So if you are not familiar with this figure, it's more clear here. So if you are given this point, you'll probably classify this one as x, right? And if you're given here, then you probably classify this point as circle, as 1. So, and in fact, this is what you can do best. You cannot do better than this classifier. It's theoretically optimal. So that's why this simple classifier is called the optimal base classification. So you'll always get this error. If your probability density for class 1 and class 2 kind of overlaps, then you will always have this area, which is the amount of error you get. And you cannot achieve better performance than this one. So you cannot get 100% accuracy or 0% error, always. Because as long as these two distributions are overlapped. That's what the optimal base classifier said. And actually, you need to adjust a little bit to be a Bayesian. So, in fact, what we want to compare is not the P of x given C, but P of C given x. So, using the Bayes rule, P of C given x is P of x given C, P of C over P of x. And this is not relevant, it's just a normalizing constant. Because we are only considering C, and here you don't have C, so you can just consider this one as just a normalizing constant. So, if P of C is equal for class 1 and class 2, then you can just compare P of x given C as I drew here. Just compare P of x given C. But if you have some kind of prior knowledge on the class, that so if these two classes are the cancer, so if it's class 1, it's cancer, and if class is 2, then it's not a cancer. It's error. Then you maybe have some kind of prior knowledge that normal people doesn't have cancer, right? So maybe you set P of C equal as 0.9 and P of C equal to 0.1. Right? Then this shape will be scaled according to these values. If you don't have any prior knowledge, you can just set this to equals to 0.5, then you can just remove PC because it's basically the same. So you can just compare P of x given C as I wrote here. It's just a simple classifier. And you cannot achieve better than this classifier. And one problem is you don't know this distribution. Right? If you know this distribution, you're done. Right? You don't have to train a model. If you know this distribution, you have optimal classifier. Yeah. It's theoretically optimal. Any of the model can do better than this. Cannot do better than this. And but the problem was we don't know this distribution. As I written here, we don't know the input distributions. So what we can do is first estimate this distribution from the training data. We don't know the PDF, but we can estimate the distribution, conditional distribution of P of x given C equals to 1 and P of x given C equals to 2. And you first estimate the distribution and compare, and you do the optimal Bayes classification. So what you need to do is estimate the probability density. And roughly there are two ways. First is non-parametric methods. And second is parametric method. second one is more familiar. You assume that your probability density distribution is a family of Gaussian distribution or family of uniform distribution, or there are many different kind of distributions, Laplace distribution, or many different kind of distribution, or Gaussian mixture distribution. And those are all parametric. It's parameterized by, for example, for Gaussian, it's parameterized by mean and variance, two parameters. But for the first case, we don't use any parameter. So how do you do it? So I'm going to talk about for about 10 minutes what the non-parametric density estimation methods are. So I'm going to talk about two methods. First one is kernel density estimator. Called KD. The second is KD estimator. I think many of you know K-nearest neighbor as just a classifier. Actually, it's in the first place, it's a density estimate. You can get the KNN classifier from KNN density estimation, and if you estimate the KNN estimate the probability density with KNN, then if you do optimal base classification after, then you will get the KNN classifier. So these two are most famous non-parametric methods, and these two shares a very simple concept. So let's just consider the task. Just forget the classes, and you have just this kind of data points here. Then where is the region that the density is high? Here, density is kind of smaller than this region, right? That's what density means. Here, dense is not dense. And if you want to estimate for this point x, this is a two-dimensional feature space. And if you want to estimate the density here, what you can do is calculate this number. P of x is n over k, n over v. So, if you have n number of data, and near this point, this inspection point, you consider k number of points. I mean, roughly speaking, you have a number of data, and you take this kind of region, this volume is V. Then if you have many number of data in this volume, then the density is higher, right? So that's why K is the upper side. 분자에 K가 있는 이유고. If K is bigger, then your density is higher, and K is like, but here K is just arbitrary amount, so you need to normalize by the total number of data. So you need to divide by n, and also if you increase the volume, then you will get any number of K, so you need to divide by 3 as well. So this is very simple density estimate. And this is the core principle shared by these two algorithms. And if you integrate this number over a whole space, you'll get 1. Right? You can simply summarize all this, then you'll get the total volume. If you summarize the case, then you'll have n, so it's divided. You'll get 1. So it's very simple, but it's working density estimator. So what you're given here is n is fixed value, right? If you have trained data set, you have n number of data, and n is fixed. You can do nothing about n. But you can change v and k. So if you increase v, then you have many number of data, many number of samples. If you increase v from here to here, you have more number of data. So in parallel with the VC inequality, you have many number of data, you have a smaller variance or smaller error, right? It's more, you can be more confident on the density because you have seen more data. But if you increase V, then your spatial resolution will be poor, right? Because you increased it. Maybe the probability density is can be like this. If you increase your V, then you only get a very smoothed version. You lose the spatial resolution, right? So if you want to reduce, so there's a big trade-off. If you want to reduce the variance, you need to increase the volume. But if you increase the volume, you will lose the spatial resolution. Right? But if you make V very small, then you will get 1 or 2 samples, then your variance will be very high. So you need to compromise between V, small V and large V. You can do. Are you following? So for kernel density estimator, for KDE, what we do is fix the V. Fix V and calculate K. So the most basic one is parts and window. it's very simple. Your inspection point is here, and partition window is like this. That's 0. Use this partition window, which means we're going to compute this one. So you fix V, which means you fix the width. So I just mentioned that we need to compromise the volume, right? And define volume. And here you fix the volume here with the value you like. Here I chose the value h, the window width, and so you choose the volume, then you can count the k, right, in this point. So if you have in single feature, for single feature, if you want to inspect this point, and if your data is like here, you can count the number of data points in your window or in your volume V. And here it's 3, so you can calculate k into 3. Right? It's very simple, right? So in equation, your probability density in P of x is like 1 over n, and summation, use the summation, then n equals to 1 to large n of kernel k x x n. So the kernel k x x n equals to 1 if smaller than otherwise. This basically means that you want to count if the data is in this region, but you don't want to count otherwise. So, and this is partition window kernel. So let's just repeat again. So you are inspecting this point x, and you want to estimate the probability density at this point, and you set some sort of fixed window, and you just want to count only the data, number of data in this region. So you define this partition window kernel, which is basically 1 if the data is inside of this region, and 0 if the data is outside of this region. And you can consider this the same equation from the point of view, from the xn point of view. Here I use x point of view, but if you consider it an xn point of view, then your whole distribution P of x is like this. So if your data is here, then you can just use this kernel to add. And as this one is, you have some overlapping window, then your density will be like this. And there's also overlap the density will be like this. If you're thinking from X point of view, then you're just counting the number of data in this region. But if you consider that this kernel is presented at each training data set, training data, then you just use the kernel and just add them. 무슨 말인지 그러니까 그냥 X 입장에서 봤을 때는 그냥 여기서 카운트하면 되고 그걸 모든 엑셀에서 한다고 생각하면 그냥 모든 트레이닝 데이터에다가 이렇게 커널을 씌우면 돼요. 이렇게. 그래서 그냥 커널을 쭉 더하는 거죠. 이게 8.2도 커널로 커널 덴시티 에스티메이션 할 때 나오는 거고 근데 이렇게 하면은 우리가 별로 원하지 않잖아요. 스무스한 걸 원하잖아요. 그럴 때는 이제 이걸 스무스한 버전이 So this is not so good because it's kind of rectangular. It's not smooth kind of probability density. So to smooth this density function, we replace the Parson window kernel to Gaussian kernels. So that's Gaussian kernel is a kind of standard kernel we will use for kernel density estimation. So Gaussian kernel will be, I think everybody knows that it looks like this. Right? If you use this kernel, then you use for each point you use a Gaussian function, then you will get some smooth estimation of the probability density. 시간이 좀 적어지고 있을 것 같으니까. So for KDE, you fix V and calculate or count the number of data points. But in K-nearest neighbor, you fix K and calculate the V. It's very similar. So you can think of this method as kind of adaptive kernel density estimator, because your volume is adapted according to the current samples. So what this is doing is that, if your inspection point is here, then here, and your data is like this, and if you set k, okay, k equals to 3, then you measure the volume. So this is the most nearest one, and the second nearest, and third nearest, and you take this volume. And you can just substitute V here, and K is fixed, so it's very simple. That's this. It's much simpler than kernel density estimator because we don't have to choose the kernel. You just compute the volume where the kth nearest neighbor occurs. And from here, I'm going to, so I was talking about the optimal base classification, and optimal base classification is the theoretically optimal classifier, but you don't know the actual underlying density function. So what you can do is estimate the probability density for each class first, then do the optimal base classification. So there are non-parametric and parametric methods. I'm talking here only the non-parametric methods. The first one was the KE, and second is KNN. And what I'm going to do from now is use KNN to estimate the density function, and then do the optimal base classification. So for optimal base classification, what we need to calculate is these three terms, right? So PC x equals P, x given C, P of C, and P of X. So there are different classes of data, and if you somehow estimate the probability density like this, and there's an error that you cannot reduce, which is Bayes error, and you classify this part as class 1 and this part as class 2. So for a K and N, this number, what is this number? It's just a P of X, and it's K over NV. So we already set K, or let's say K equals 5. K over number of data is fixed, and volume is fixed. It's just then K over N3. And what is the prior distribution for C? If you have n number of data, and for class 1, n1 number of data. So if you have 100 number of samples, and 30 of the sample is circle and 70 is cross symbol, then you have just 0.3 versus 0.7 prior distribution. So it's I'll just write down as NC over N. And for this one, you already know, you're already given the class. So there's NC, number of data you're calculating, and the volume is the same, and the number of data is KC. So this one is NC over N, this one is K over NV, and this one is KC over NCV. So then, if you compute this one, and N goes away, V goes away, and C goes away. Then what you get is KC over K, which means that for your inspection point here, you look at 5 nearest neighbor points. 5. This K is K equals to 5. And if the number of data for class 1 is 3 and number of data for class 2 is 2, then you just take the class 1 because it's 3 over 5 versus 2 over 5. That's the K nearest neighbor classifier. If you have any question, if you don't have any question, I will stop here.
네.